Hello, calculus students. Here we are with antiderivatives and indefinite integration. And basically, this is going backwards from what we've been doing before. We're going to learn these skills, write a general solution of a differential equation, use indefinite integral notation for antiderivatives, use basic integration rules to find antiderivatives, and find a particular solution of a differential equation. Okay. Now, let's suppose you're asked to find a function f whose derivative is 3x squared. From your knowledge of derivatives, you know you would probably say that, well, it's x cubed, because the derivative of x cubed would be 3x squared. This is called an antiderivative. Definition of an antiderivative. An antiderivative, big F, is an antiderivative of little f on an integral if the derivative of big F equals f of x. So that's, therefore, f is the antiderivative. So look at these examples of some antiderivatives here. We've got f1, big F1 of x equals x cubed, big F2 of x equals x cubed minus 5, big F3 of x equals x cubed plus 97. If you take the derivative of any one of these, you'll get 3x squared. The derivative, f prime, f1 of x equals x cubed. The derivative of f1 of x equals 3x squared. And that's equal to our f of x. So we're going backwards, and we're going to have a lot of practice with this. And how do we represent derivatives? Notice in the last problem that we had several examples, look back, where basically they were all antiderivatives. They just differ by this constant here, and that's called the constant of integration. And that's the c here, this constant. You got to remember to add that on when you're going backwards, because you lose some information. Basically, all these parabolas, y equals x squared plus 2, y equals x squared, y equals x squared minus 3. When I take their derivative, you get the same thing. You get 2x, 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 because the constant term falls out. So when we go backwards, we're going to have to reintroduce that constant term and say, well, we have a little uncertainty here. We'll need more information about the original function to narrow down what that constant is. So we're going to explore a little bit and try to see if we can do some antiderivatives here. Okay, the derivative of big F of x is 2x. What do you suppose you took the derivative of to get 2x? Well, x squared, right? Because you bring the power down in front and lower the power by 1. Now notice we're taking the process in reverse, though. So instead of dropping the power, we're increasing the power. So I can't just say here, for the antiderivative, calling it x squared again, because if I take the derivative of x squared, I'll get 2x. So I have to take this answer and divide it by 2. So now when I take the derivative of this, I'll get the 2x. It'll cancel out with the 2, and I'll just keep plain x. Similarly, here's x squared. It must come from x cubed. Someone took a derivative of x cubed, but if they did that, they would get 3x squared, so we got to divide by 3. This one's x to the negative 2. So the next power up is x to the negative 1. If I take x to the negative 1 do its derivative, I'll get negative 1 x to the negative 2. There's an extra negative in there. I've got to divide by that negative 1. See how we're constantly dividing by the new power? That's going to be part of the rule. Here's x to the negative 3. One power up from that is x to the negative 2. Now, if I'm going to take the derivative of big F to get this, the negative 2 will come down in front. This will drop by 1. Negative 2x to the negative 3. But we have no coefficient here, so we have to divide by the negative 2. So hopefully you're getting the idea of what's going on here. Now, we've, up to this point, been doing differential calculus, where you're given a function and you find its derivative. Now we're going backwards. We are taking the derivative function and trying to figure out what the original function was. So it's called an antiderivative. Now, you can represent the whole family of antiderivatives just by adding on this constant c. So, if the derivative with respect to x of x squared is 2x, you can represent the family of all antiderivatives f of x equals 2x by x squared plus c. This c is also called the constant of integration, and this is the general antiderivative and general solution of the differential equation, because this is a differential equation because it has a derivative in it. It involves x's and y's, and it can also involve it has to involve the derivative of the variable. So y prime equals 3x, that's a differential equation, so is y prime equals x squared plus 2, x squared plus 1. Now, we're going to keep the differential equations pretty much solved for y prime for now. as you take, there's a whole course in college called DiffEq, differential equations, where you solve more complicated things that have mixes of x's and y's, and maybe even first and second derivatives, so it can really get pretty extreme. Solving a differential equation. Find the general solution of the differential equation y prime equals 2. So we write down y prime equals 2. And so I'm going to take the antiderivative of both sides. Now, get used to this notation. Remember how we said y prime is also dy over dx equals 2? I like to write it this way and put the dx over here, and then take the antiderivative with respect to of dy equals the antiderivative of 2 dx. Now what this does then, this notation, let me go to split screen here, is the antiderivative of the derivative, you just get y. The antiderivative of 2 dx, well, 2 is just a constant. This means that the derivative of the function is 2. That means the slope is always 2. Well, that's a line. So it's 2x. Notice how where the x appeared from? It's because we basically had x to the 0 power and we're cranking it up a power to 1. Now we have to add on the constant of integration, because any line with a slope of 2 will have a derivative equal to 2. So there's your first differential equation. Let's try another one. Oh, and here's the example of all the things in the whole family of these general solutions. Any one of these lines has a derivative equal to 2. They might all look different, but notice how they're all parallel. Now let's talk about some basic integration rules. Here's that notation I talked about. When you do a derivative, remember how when you do a derivative you have that with respect to x here? That with respect to x comes in right here now in our antiderivative symbol. And basically it's not a division anymore, it's a multiplying. And we're going to study this as it will help us find areas under the curve. Just like the derivative is helping us find slopes, which is a sort of a division idea. Now, since integrals are the reverse process, integrals are going to help us find areas, which is a multiplication idea. Okay? And if you take the derivative of an integral, you're back to the original function again. Here's some basic integration rules. If you take the derivative, you remember the derivative rules? You take a derivative of a constant, you get 0. You take the derivative of a constant multiplier, it just comes out. You just get k because it's like the slope of the line. If you take the derivative of a constant times a function, the constant kind of comes on outside the derivative notation. And here's the derivative of a sum, is the sum of the derivatives. And here's our power rule. This is the one that comes in the most here, x to the n. The power comes down in front, and x gets lowered by a power. Now notice what happens here though. If you take the antiderivative of 0, you get a constant. In fact, you can think with any expression, any function, you could add 0 on the end, and that's where that constant integration is coming from. Antiderivative of a constant times x is kx plus c, and you get a line. If the derivative is constant, that means the slope is constant, and you have a straight line. Integral of k f of x dx, the k can come outside the integral notation just like it comes outside the derivative notation. Notice there's no plus c down here because we haven't done this one yet. And you can't, just as you can distribute derivatives over addition and subtraction, you can distribute antiderivatives over addition and subtraction. Now here's the trick. Here's the new version of the power rule for integrals. Antiderivative of x to the n. Remember that problem where I kept on cranking up the power because we're doing the reverse process? But then you have to divide by the new power. And don't forget your constant of integration. This always works as long as n doesn't equal -1, because then you're going to be dividing by 0. So we're going to have something later on to figure out how we're going to take an integral of x to the -1. So one of the things that strikes me between the difference between these two rules is it's the order in which you do the process. And let's take a careful look at this. Look at these two rules. You got the derivative with respect to x of x to the n equals n times x to the n minus 1. Versus, let's just do this on split pages here. Sorry. X to the n minus 1. Let's go over that example again. Let's say you had y equals x cubed. The derivative would be 3x squared. Notice what you're doing first. Bring down the power. And then decrease the power by 1. Okay, now contrast that with antiderivatives. And let's look at our notation on here. Antiderivative of x to the n dx. Antiderivative of x to the n dx is x to the n plus 1 divided by n plus 1 plus the constant of integration. So let's say you're trying to take the antiderivative of x cubed dx. You don't get 3x squared. Instead, you get x to the 4th divided by 4 plus the constant of integration. Because basically you have to do it in 2 steps again. But you're going to do the steps in reverse order. So if you brought down the power and then decreased it by 1, now you're going to take this reverse process, you're going to increase the power by 1, and then divide by the new power. And that's how it's got to work, because you're undoing a process, and you're taking the reverse of each of those ideas, but you have to do them in reverse order. So, describe the antiderivatives of 3x. Well, the antiderivative of 3x dx is we're going to crank it up power. First of all, this 3 can come out in front. It's a multiplier. And now we crank up the power in x to the first, so it becomes x to the second, and divide by the new power plus the constant of integration. So there you go, 3/2 x squared plus the constant of integration. There are a bunch of parabolas with happy parabolas with a of 3/2, but they have different y-intercepts. And there's the notation that we're going to use. And now, here's a little something to be careful of when you're doing your integrating. Rewrite it first, just like when we did derivatives. Get it as x raised to a power first. So if you've got a radical or a fractional power, get them written as powers, x to the negative 3. Now you can crank it up. And remember, 1 up from negative 3 is negative 2, and you divide by the new power. X to the half, 1 up is x to the 3/2, and divide by 3/2. And then simplify. Okay, integrating polynomial functions then. The integral of just dx, when it's just like that, it's kind of like x to the 0. But you just know that this is x plus the constant of integration. Because basically we started with x, you didn't see an x there, it's x to the 0 power. So you're cranking up the power 1 and dividing by the new power. X all over 1, or just x. So I just gave a little more explanation, but you don't have to do that every time. If you just see this integral of dx, that just ends up being x. See how the integral symbol, the antiderivative, is undoing the derivative. That makes sense. Okay, now we can distribute the antiderivative over addition. So it's antiderivative of x dx plus the antiderivative of 2 dx. So here we crank up the power by 1 and divide by the new power. The two constant come out in front, and we just said the antiderivative dx is just x. But don't forget that constant of integration. Here we go, crank them all up. Antiderivative of 3x to the 4th, you can distribute the antiderivative over the idea of addition and subtraction, plus antiderivative of x dx. So the constant multipliers come along for the ride. This is x to the 5th over 5, plus the opposite of, bring along the 5, x to the 3rd over 3, plus crank up the power of x to the first here by 1, x to the 2nd over 2, plus your constant of integration. 3/5 x to the 5th minus 5/3 x to the 3rd plus 1/2 x squared plus c. And there's no point adding all these, or trying to combine them in one fraction. That's fine. Keep them separate. Now, here's an example of rewriting before you do the integrating. Because there is no quotient or product rule for antiderivatives. We had a special rule for derivatives, and you could use that on derivatives, but there is no such rule for antiderivatives. You're just going to have to hope you can separate everything by addition and subtraction. And so that's what we're going to do first here. We're going to rewrite this as x over square root of x dx plus antiderivative 1 over square root of x dx. And so this is x to the first and this is x to the half, so when I subtract the powers I get x to the half, so I get x to the half dx plus the antiderivative of x to the negative a half dx. So crank up the power by 1, add 1 onto the power, and divide by that new power. Plus x to the negative a half plus 1, divided by negative a half plus 1, plus the constant of integration. Now, I showed this step in here, but you can add them up in your heads too. I just want to be really emphatic about that's what's kind of different about integrating. This same power shows up here and here. Whereas when we're doing the derivative, we decrease the power after we move the power down in front as a multiplier. Now you're going to increase the power and then move it down as a divider. So it's x to the 3 halves over 3 halves plus x to the 1 half over 1 half plus constant. And so that's 2x to the 3 halves over 2 plus 2x to the 1 half plus c. That's fine. You might say, oopsie, no, that's not fine. I should have, oh, that's over 3. Yeah. Some people like to rewrite this as a square root. It's not necessary. Okay. And this is what I just talked about. Do not integrate the numerator and denominator separately. There is no such rule. Okay? You can't do that. Can't do that. Okay, now initial conditions and particular solutions. Notice if I've got dy dx equals 3x squared minus 1, we can go ahead and try and find the antiderivative, but you get x cubed minus x plus c. And this is called the general solution because there's many possible functions that can have this as its derivative. Now, if someone gives you some more information, now maybe you can narrow it down. So in this case, we can get a particular solution if someone gives you some initial conditions. That is, here's the general solution, and someone tells you that goes to the point 2, 4. So you can put 2 in for x and 4 in for f of 2 and solve for c. You get c equals negative 2. And that creates your particular solution. Notice the difference. General solution is a whole family of answers. Particular solution is a specific subset of that family, one element of that family, that satisfies the initial conditions. And here's an illustration of all the x cubed minus x plus c's. This is just a few of them and all the different constant variables. Okay? They all basically have the same derivative. F prime of x, no matter what you're looking at, is 3x squared minus 1. And the derivative constant is 0. So all these have the same derivative. Now find a particular solution. Find the general solution first of this equation, and then find the particular solution that satisfies the initial conditions, f1 equals 0. So I'd like to write the derivative as dy over dx equals 1 over x squared. So you get dy equals, this is x to the negative 2 dx, and I'm going to take the antiderivative of both sides. So we get y equals x to the negative 1 over negative 1 plus the constant of integration. So y equals negative 1 over x plus c. This is the general solution. General solution. But now use f of 1 equals 0. That is, it's giving you the point. If you put 1 into the antiderivative, you should get 0 out for y. So we've got to make 0 work in this. So put 0 in for y, put in 1 for x, and so 0 equals negative 1 plus c, so c equals 1. So now we have y equals negative 1 over x plus 1. This is the particular solution, because someone gave us the particulars. Okay? Oopsie, I went the wrong way. Uh-oh. Maybe I accidentally added a page somewhere. Hold the bus. Yeah, I put this in the wrong spot. I'll move that later. So, now on to kinematics problems from physics. Remember how velocity was the derivative of displacement? And acceleration is the derivative of velocity? And that's what we did in chapter 5. When we were doing applications, we'd start with displacement, do its derivative, and get velocity. Once you had velocity, you could figure out acceleration. Now in chapter 6, now to get at displacement, you're going to start with the acceleration, do its antiderivative, and get the velocity. And once you have velocity, you can do its antiderivative to get displacement. And you'll need some initial conditions on all these. And sure, that's what we have here. A ball is thrown upward at initial velocity of 64 feet per second and initial height of 80 feet. Find the position function given the height s is as a function of time. Now what you'll be given in this is gravitational acceleration. G equals gravitational acceleration. And in this system that's negative 32 feet per second squared. I don't expect you to memorize that. I would have that as part of the given information. But basically then, you're told that acceleration equals negative 32. Acceleration is the derivative of velocity with respect to time. So that's equal to negative 32. So we're setting up for a first differential equation here. dv equals negative 32 dt. And I'm going to take the antiderivative of both sides. Let's get a little, we need a little more space. So the antiderivative of dv equals the antiderivative of negative 32 dt. So v equals negative 32, the constant just kind of comes right outside. The antiderivative of the derivative t is just t. And don't forget your constant of integration. So there's a velocity equation, but it's a general velocity. Any one of these would have a acceleration of 32, because I take the derivative of this velocity, I'll get negative 32. So I have to use this, the initial velocity of 64 feet per second. Initial velocity, sometimes known as v naught, is equal to 64 feet per second, and it's thrown upward, so it's positive. So initial velocity, that means the velocity equals 64 when time equals 0. So basically, you're given this initial condition. You can use it to figure out what c is. So put 0 in for time, negative 32 times 0. Put 64 in for velocity, and you can see we get 64 equals c, so c equals 64. So now we have the particular solution. Got to make another page again. Now we have that velocity equals negative 32t plus 64. Now to get the equation itself, remember that velocity is the derivative of displacement with respect to time. And I think they're using s for displacement here. So that's equal to negative 32t plus 64. And let's put the dt on the other side there, just so we've got all our eggs in a row. Take the antiderivative of both sides. And now you get s, the displacement, equals negative 32, crank this up, t squared over 2, crank up 64 as a constant, so now it's going to be multiplied because it was t to the 0, now it's t to the 1, plus a constant of integration. So s equals negative 16t squared plus 64t plus some constant of integration. Now we can use initial conditions to get the specific answer. The initial conditions. And that's basically that at time equals 0, it says from an initial height of 80 feet. So you're just throwing this ball up. So the initial height, s naught equals 80. So that means s equals 80 when t equals 0. That's why we often put the little subscript 0 there. So we can put 80 in for s and 0 in for t. That's why it's nice if the initial conditions involve a 0 with much less arithmetic then, because these fall out and you get 80 equals c. And so now you have the particular solution, s equals negative 16t squared plus 64t plus 80. If this seems familiar, this whole idea of plugging stuff in, remember that's what you're doing with the old y equals mx plus b form. Someone would tell you the slope of the line, m, and then you'd put in one of the points to figure out what that constant b was. And that's kind of like what we're doing here. And so there's the equation, negative 16t squared plus 64t plus 80. And to get the particular answer here, the height of the ball at time t, that's what it looks like. I think the question asked was in two parts though. When does the ball hit the ground? We've got the position thing, when does it hit the ground? So to find out when the ball hits the ground, we're going to need another page. Part B, when is h, or the displacement, equal to 0? So this is in calculus now. This is a review of solving a quadratic like this, 64t plus 80. I think you can see that you can divide through by 16 goes into all these. Let's divide through by negative 16. We get t squared minus 4t plus 5. So it's t minus 5. Oh, did I do this wrong? Oh, yeah, t. Negative 5, yeah. missing something here. They're getting t equals 5 here. 16 out of 80 is 5. Oh, it's a negative 5. Oh, you silly goose, Mr. Lang. There we go. Negative 5. So it's t minus 5 times t plus 4 equals 0. So t equals 5 or t equals negative 4. And only this one makes sense in our situation. Negative 4 is acting as though it came back here. Or, I'm sorry, negative. Oh my gosh. This is a t plus 1. There we go. T plus 1. Time equals negative 1. Okay. And we don't look at the negative time in this particular problem. Just t equals 5 is when it hits the ground. Now, here's just a little review of the importance of rewriting the integral as just x to 1 power. Or, yeah, in this case, like t squared plus 1 squared. We don't have any general power rule for these either. You're going to have to expand that out. Divide this x squared into each. Distribute the cube root of x into each and have them as fractional powers to do the integral. Okay, flange out.